When I see the northern lights, I see life. Hi, my name's Alex. I've argued enough for a lifetime. Put your headphones on, sit back, relax, and enjoy your commute or whatever else you're really doing right now. Good night to those of you who use my content to fall asleep. In addition, please share and like or give a thumbs up or do whatever one does on the platform you use to consume content like this. Doing so will help me a lot. Thanks. The northern lights, that green velvety curtain dances over the sky, inspiring countless stories of everything from dark warlike gods awakening to ancestors playing football with enemy skulls after the war, and poetry of wars too, I'm sure. This story is not that story, even though I appreciate the legends which aren't just about war, by the way. I still can't quite wrap my head around the idea of the lights dancing. Now, I'm not dismissing the idea. Both the legends and the imagination that comes with them are too beautiful to not warrant their own piece at one point. No, it's not that. To me, there's just something much bigger to uncover than legends and dancing. And all you need to do to get there too is to stay with me for a while. Hop over whatever physics distresses you, but also take away whatever physics you do find comfortable to think about. Challenge yourself. Follow me. Den tingen som du ofte har spurt om, hva det kan være som grønlendingene kaller nordlys, det er jeg ikke så særs kynnig i, og jeg har ofte råka folk som har vært på Grønland i lang tid, og de synes ikke ha fullvis kunnskap om hva det er. Ellers er det slik med den tingen som med de fleste andre som folk ikke kjenner med visse, at vittuge menn gir seg en mening og gissing om deg, og tror slikt om det som syntes deg vanligast og rimeligast. Den naturen og hotten er det med nordlyset at det er alltid så mye lysere som natta i seg sjøl er mørkere, og det synes jeg alltid om natta. Men aldri om dagen og oftast i koldmøre, men sjelden i måneskinn, og det er såleis å sjå som en ser en snor laga en svær eld langt unna. Det ser ut liksom det fra denne skytkvasse oddar opp i lufta, ulykke på høgd og mye urolige, så at snart kjem den ene høgst og snart den andre, og alt dette lyset skifter såleis at det er som en blakrande kige å sjå til. Men medan disse strålene er på det høgste og bjartaste, da står det så mye lys av deg at folk som er ute kan godt fare sine veier, og like ens gå på veiding om det trengde. Og om folk sitter inne i husa sine og så sjåenlig over jorden, da er det så lyst inne at alle som er i huset kjenner hverandre. Did you understand anything? If yes, you're probably a little miffed at my pronunciation of this, say, rather vintage edition of Norwegian. Yes or no, it's all good though. The point is that there were texts such as this, the King's Mirror, which discussed the Northern Lights in more or less academic terms in the 13th century. And what I just read for you was part of an educational dialogue between father and son, starting with, "You know the thing you always go on about? Yeah, neither me nor all the wise men really know what it is, but make no mistake, we're studying it, and we've got some ideas too." That's it, basically. In other words, they were asking questions about the Northern Lights, and they were looking for answers too. One of those questions was, where do the colors come from? As in, forget the stories, what really happens here? Today we know the answer lies in quantum effects involving atmospheric particles colliding with electrons and ions. It's about energy exchange. It always is. I mean, collisions are never easy to handle properly, but they can always be understood in terms of energy exchange. Imagine a car crashing into a wall. The energy of the car's movement will, at the end, be used to deform the car, and perhaps the wall a little too. In quantum collisions, the energy of the incoming particle will, at the end, be used to create a photon. Light, that is. There are a couple of steps in the middle there. The atmospheric particle absorbs the energy first, then gets rid of it in the form of light. And that's a good thing for us, because the color of the light sent out is characteristic for the respective atmospheric particle. Like, we will know what sent out the light. Oxygen atoms, for instance, can only radiate particular types of green and red. Well, no, quantum theory gives other opportunities too, but those other colors we can't see, or they are not intense enough for our eyes to detect. Still, we know that northern lights in photographs usually show oxygen atoms. Now, granted, we're not talking about large amounts of energy per collision, but then once in a while, 1 billion of these collisions occur at the same time at the same place because there are just that many particles in the atmosphere and a comparable amount of other ones streaming in. Thus, the sky lights up. Wait a second, streaming in? So we're talking about particles from the outside, streaming into the Earth's atmosphere. And if they are on the outside of Earth's atmosphere, they are on the outside of Earth's magnetic field. That's relevant because most of the electrons and ions we're thinking of just wash by Earth, thankfully. They can't get into the atmosphere because of their interaction with our magnetic field. Yet sometimes some particles enter the Earth's magnetosphere, as it is called, which wraps around the atmosphere like a just slightly imperfect electromagnetic shield. The physical process behind that imperfection is called magnetic recombination. It's wonderfully absurd physics. I mean, one way to describe it would be to say that magnetic fields melt together under the right circumstances. Not too often though, only sometimes. It's got to do with what is called Alfvén's theorem and frozen-in magnetic fields. Well, think about it this way. One can assign so-called field lines to magnetic fields. The idea is to draw a line where a charged particle would move, kind of. The particles usually follow a sort of helix track. The center of that helix movement would be where we draw our magnetic field line. Got that? It's school physics, but probably a part of school physics you, like me, wanted to forget as soon as it was possible to do so. Still, magnetic recombination is a process during which these imaginary field lines realign. Only that means that the particles move differently in all senses. They'll have a different direction and they'll also be much faster than before. So as weird as this is, the process of imaginary field lines realigning has quite real consequences. It comes down to energy exchange. Yes, this too. See, it turns out that magnetic fields have what is called potential energy. You probably know the term from school again, but if you don't, the idea with potential energy is that if you ain't doing something about it, stuff will happen. You ain't holding up that apple, it'll fall. That kind of thing. The electrons and ions push against the Earth's magnetic field, which holds on until it can't anymore. The can't anymore, quote-unquote, happens under very specific circumstances, but when it does happen, the proverbial apple will fall, and in this case, charged particles will not just enter the Earth's atmosphere, but will accelerate along the field lines of the Earth's magnetic field and be there to collide billions of times at the same time and at the same place with atmospheric particles. Alright, where do those charged particles come from then? Honestly, where do those charged particles come from? And what did I mean by most of them washing by Earth, thankfully, quote-unquote? The truth of the matter is that the Sun constantly sends out electrons and ions. The solar wind is a steady stream of electrons and ions emanating from her, from the corona to be precise. It fills the whole solar system. It's enormous and can obliterate the environment on a planet. Look at Mars. It used to have a magnetic field. It used to have an atmosphere too, and we think liquid water and all that. But it doesn't anymore. Why? Because it lost its magnetic field, and without it the solar wind was free to quite literally blow the environment on Mars away. This also means that the Sun loses particles, constantly. Yet that doesn't really matter. There's just too much matter in her for this to make a difference. She's 1.4 million kilometers in diameter, after all. Now, there is a little detail to everything I just said a minute ago. We wouldn't see the northern lights if that was the whole story. No, in order to produce aurora, the solar wind needs to be enhanced, made stronger so that it can push against Earth's magnetic field enough for magnetic recombination to happen. But no worries, the sun's surface explodes once in a while, you know? That very same process, magnetic recombination, happens on the sun too, when her magnetic field turns in on itself and creates these wonderful loops you can sometimes see on TV or online. When the loop becomes too tight at the bottom, the whole thing can explode. At the base of these explosions are what is called sunspots. You've heard about them, surely. Wait now, why would the sun's magnetic field turn in on itself like that to begin with? Because it is created by particle streams under the surface which are quite literally convection streams, like the thermics eagles use to soar up high into the atmosphere. Particles stream upwards until they cool enough to sink down again. Of course, particles here are electrically charged too, and that produces a magnetic field. The problem is that the sun doesn't rotate at the same speed everywhere, so those convection streams get distorted after a while and can ultimately lead to exploding loops of plasma, so-called solar storms. Okay, now, the question is quite apparent. Why doesn't the sun rotate with a constant speed everywhere, like Earth does, for example? See, when the sun was born, she drew in matter from a disk of rotating stuff. That disk blobbed in the middle, kind of, is what I'm saying. And on top and bottom of that bulge, the rotation slowed down a tad. The blob became the sun, and her rotation follows the same pattern still. Faster rotation in the center, slower rotation at the poles. The difference is around 10 days per rotation, or thereabouts. And the particle streams which create the sun's magnetic field get twisted by that weird difference in rotational speed. In addition, in thermics, the rising air cools down and sinks again at one point precisely because it gets colder higher up. With lower temperatures comes lower pressure too, and that's because of lower density. Turns out in the sun everything is determined by density. The further down you go into the sun, the denser she gets. In fact, in the center she is so tightly packed that the ions there, it's a plasma, ionized gas really, fuse together to become other ions. Hydrogen becomes helium, if you're wondering. When I was teaching, there was always that one student, the one who would be rather annoyed at this point and say something along the lines of, "Okay, what's next? Are we going to talk about where hydrogen comes from too? I thought this was about the northern lights." You know how hydrogen was made, right? Turns out we can take this all the way to the beginning of the universe. Do we want to? I kinda do, but then we can also just turn around and think about northern lights in a more usual sense. I mean, on TV or online this story is usually, quote-unquote, told the other way round. And no, we don't start at the beginning of the universe. We start deep inside the sun, in her core, where hydrogen fuses into helium, releasing energy that to start with has nowhere to go. So it pushes outwards in the form of radiation until it gets just a little more space and starts accelerating particles which then form convective currents, pushing upwards and outwards. This can take several hundreds of thousands of years, by the way, until energy breaks free into the solar system in the form of light and, of course, the solar wind. Truth be told, the solar wind is always there, but sometimes when explosions happen on the sun, it has a little extra oomph in it. And when that happens, there might just be a visible aurora on Earth a couple of days later because the extra pressure might make Earth's magnetic field give way just a little. So, some of the solar wind may enter the Earth's atmosphere. Its particles colliding with the atmosphere's atoms, ions and molecules. And if this happens often enough, a couple of billion times at the same place and the same time, we can see the light created by these collisions, the aurora, standing there in the middle of nowhere, looking up and pondering. And thus it is. Whenever I look up, I see the colors in the Earth's atmosphere. I see Earth's magnetic field lines being made visible by those lights. And I ponder. I ponder the energy from the sun. Atmosphere, magnetic field, solar energy. Those are the ingredients of aurora. Without them, there is no aurora. But this is, in a very real sense also, the triumvirate of life on Earth. Take away one of them, and we'd all be dead. Or more likely, would have never come into existence. When I see the northern lights, I see life. Thanks for staying with me to the end. Join me on socials and YouTube, or check out kindnessthrough knowledge.com to book a presentation. See you next time.